Okay, welcome back to section 4.1, vector spaces and subspaces. Okay, so many mathematical structures behave like Rn without actually being equal to Rn. We'll give examples of this in a sec. And the idea is sort of try and capture what I mean by behaves like, capture these relevant properties of Rn inside of such structures below. So a vector space, so we're defining here, a vector space is a non-empty set V of objects called vectors that have two operations. You can add vectors, and you can multiply vectors by real numbers. And they need to have these two operations subject to all the following rules or axioms below. So for all vectors U, V, and W in V, and all real numbers C and D, the addition operation should not take us outside of V. So if you have got two vectors, their sum should also be in V. The sum shouldn't matter which order they come in. It shouldn't matter how you parenthesize a triple of vectors that you're adding together. We want there to exist some kind of zero vector with this property that you'd expect from a zero vector, that when adding it on the left or the right, it's equal. You just get back your vector V again. Oh, I guess since we already said it doesn't matter which order, we can actually just eliminate one of these, since we'll get the other one from using number 2 here. We also want there to be like an additive inverse. So for any vector U in V, there should be a vector negative U in V with the property that the sum of these two things is 0 again. For any real number, we want that if we scale our vector by C, we stay in V again. We want our scalars to distribute like we know and love. We want the vector to distribute also, as regular arithmetic would suggest. We don't want, if we multiply U by the scalar CD, that should be the same thing as multiplying the vector du by C. And also, if we multiply our vector by 1, we should get back just the vector again. So really, we've tried to capture all of the most mundane arithmetic properties of Rn and said, okay, anything that satisfies these things is looks sufficiently like or behaves sufficiently like Rn that we could run the same game we had in chapter 1, 2, and 3 on this new thing too. So you'll see this, like when I say new thing, they're really not that far away from Rn. So let's give some examples here. Okay. So the first example, of course, the most boring, for each n, for each natural number n, Rn is a vector space. Oops. Okay, fine. What about a non-Rn example? So let's let fancy P subscript n be the set of all polynomials of degree at most n. Be the set of all polynomials in one variable. Of degree at most n. So in other words, such a thing looks like this. P of x is a0 plus a1x plus a2x squared, and on and on and on, up to an x to the n. Where each of these AIs are real numbers. And I claim that the Pn becomes a vector space. And for that to be true, we need to check. I need to tell you what? I need to tell you what the addition and multiplication by real numbers are, and we should painfully check each of these 10 rules. We're not going to do that. I'm not even sure the textbook checks all of them, but we'll check 1 or 2 or something. Maybe not even that, but we'll certainly define what the addition is and the multiplication. And it shouldn't be anything so surprising, right? If we want to know what addition is, let's look at another element and add the two things together. So if q of x is b0 plus b1x plus b2x squared up to bn x to the n, p plus q of x should just be the polynomial you get by adding p of x and q of x. So it'll be, there we go, a naught, oops, q, a naught plus b naught, a1 plus b1 x, a2 plus b2 x squared up to an plus bn x to the n. So yeah, not a huge surprise that we can add polynomials. And similarly, it won't be a huge surprise that when you multiply a polynomial by a real number, you get back exactly what you think you ought to. What our regular arithmetic suggests you must get back. You're going to get back c times a naught plus c times a1x plus c times a2x squared plus all the way up to c times an x to the n. Okay, and I'll just say, yeah, we can check 1 through 10, oops, 10, to verify that Pn is in fact a vector space. Right, the zero vector here, of course, is just the polynomial that where each coefficient is 0, the constantly 0 function, if you like. Let's do some more examples. Let's do one that we could let big M, little m, comma n. So M sub little m, little n be the set of M by n matrices. Of M by n matrices. Yeah, with the usual addition and multiplication by real numbers. Yeah, we can show M little n is a vector space too. And in the next video, we won't see this right now, but the next video will show, we'll see soon, if we take, H to be the set of triples x1, x1, x2, x3, such that x1 plus x2 plus x3 is equal to 0. We'll see soon H is a vector space too. Okay, it'll be a vector space living in R3, so a vector space inside of another vector space. Okay, and we'll continue in video 2. Take care, everybody.